Okay, so in this video, we'll look at this module on linear discriminant analysis. It's this shortly called LDA. So we have seen a few classifiers already, actually a number of them. The last two classifiers we looked at were logistic regression and support vector machines. So both of them we went into very great detail. And we saw that they are kind of directly designed only for binary classification. And if you want to use them for multi-class classification, we have to kind of tweak them as class A is stressed and class B is stressed and class C is stressed, and then get the theta x or wx values for each of those models, and then pick up the class for which you have the largest of the theta x or wx values. So that's how we did multi-class classification there. Whereas the LDA, we will see that it is kind of directly designed for multi-class classification as well as for binary classification. So we don't need to really do any tweaking like we did so earlier for logistic regression and support vector machines. And also, we will notice that LDA, the complexity of LDA, I would say, does not really depend on the number of features or the number of records you have in your data set. It really depends on the number of classes that you have. Okay, so in that sense, we can say LDA is doing something like a dimensionality reduction that we'll see again in a separate module later in detail. But that will be more in the context of unsupervised machine learning. Whereas here we can say LDA is like dimensional reduction for supervised machine learning, or where you're doing more like classification rather than clustering. So here the training data set is accompanying the actual class as well. So one important assumption of LDA, the math behind that is it assumes that the features are continuous, as well as the distribution of the feature values is kind of like it's exhibiting a normal distribution, and there's less difference in the variance among the feature values. So it assumes that the variance for each of the feature values are almost the same or comparable. But and I have an example actually that shows that we could use LDA even if this last requirement is not really satisfied. That means the features could have different variants, and still we could successfully apply LDA as well for such data set as well. So it tries to minimize the intra-class variance and maximize the inter-class variance. So that means, again, basically like the decision boundary that we saw in the previous classifiers, it tries to compute some f values, we'll say the function values, and such that for data points that belong to the same class, the variation in such f values is not that much. So it tries to minimize the intra-class variance, whereas it tries to again well separate the data points belonging to different classes based on the f values. So like for the first example, we can see here. So again, this is a linear scale. So that's part of the name linear discriminant analysis. So it eventually comes up with some f value that will compute in the example. And if you plot those f values for the different data points in the data set, again, this data set has only two classes, 1 and 2. So the blue data points belonging to one class and the red data points belong to the other class. So it tries to minimize the variations of the data points for f value for data points within the same class, but still again then tries to maximize the difference, the variance in f values among data points belonging to different classes. So that's one good feature it tries to accomplish. Again, how good it can do that, it depends on the data set as well. So the first data set we will look at is clearly exhibiting a good decision boundary between the two classes. So that's why you see the f values are also kind of having less variance within the same class and different from the other class. So this is just a synthetic data set I came up with, and we will then look at the CRP temperature data set as well with LDA. So here we have two classes. It's not a spam email data set, it's a different data set. So there are 10 records totally, and there are 5 records for each class. So we will need something like this in our math later with LDA. So probability of class 1 is basically the number of records with class 1 divided by the total number of records. So that will be 5 over 10 here, so that's 1 over 2. Similarly, there are 5 records with class 2 out of 10, so that will be again 5 over 10, and that's 1/2. In logistic regression, we assign the class labels as class 1 and class -1. Class 1 is for the red class, the targeted class, or the class of interest, which is kind of also not normal class. And the green class or the normal class, the class -1, that's the convention we follow. In logistic regression, we call the red class as class 1, the not normal class, and the normal class as class 0. Whereas in LDA, we don't really need such conventions or things to follow. We can arbitrarily label the classes. The class labels are just for our reference, as you can see in the math. The class labels are not involved in any of the math with LDA. Whereas in SVM or in logistic regression, we saw that the class labels do get involved in the math behind those classifiers. Okay. There are quite a number of steps we have to follow in the LDA math. So the math is a little complicated, but it's easy to do. So if you just follow the steps and practice them, it's quite easy to do. So given the data set here, X1, X2 are the 2 features and the 2 classes. The first step is to compute the means. When I say means, because we'll be computing multiple means. First, we have to compute. We can do the means for across all the classes for X1, X2. I can do this simultaneously. I have done this actually here, but I can go over the math again. Okay, so this is the given data set. And so we can compute the mean for all classes. This is just standard deviation for our reference. So before, because as I said, the standard deviation is expected to be the same for each feature. So the standard deviation from A2 to A11 is 3.093. And for X2 from B2 to B11 is 2.71621. So they're kind of close enough to each other. So we don't need standard deviation for any of the we don't for any normalization, because we don't do any normalization here. This is just for our information that I computed the standard deviation values to show that in this data set, the features have comparable variance of standard deviation. You know, standard deviation is the square root of variance. So both may kind of similar. Now, the mean of X1 is what we are interested at. So the mean of X1 for across all the classes is basically from A2 to A11. In this case, comes out to be 5.7. The mean of X2 is from B2 to B11, that is 5.6. Then it will also compute the mean for each class so this case for X1. So basically you do from A2 to A6. So A2 to A6, the mean. Similarly for class 2, from A7 to A11 for class 2 for X1. Similarly for X2, for class 1, the mean from B2 to B6. And then for class 2, it's going to be from B7 to B11. So you have to compute the X1, X2 mean for each class basically separately. And that's what I have tabulated here. The second step is to determine what's called the means corrected matrix. So let me first write down the actual matrix. So we'll now form 2 matrices, XC1 and XC2. corresponding to the two classes. So all the data points belonging to the one particular class will be put together in one matrix. So we can just copy and paste the values here. So these values will be now XC1, which I don't put it here, but we can have it if you want. That's X. Actually, we want to have the means corrected matrix. Okay. Anyway, yeah. And we will then use that. So let me just put it here since I I would have used here itself. So this is, since I already have it, I would need to copy it again. So that's why I did put it there. Okay, anyway. Then this is the matrix for class 2. So let's just call it as XC1 if just for difference, since it's class 1. That's matrix MC1, and this is matrix MC2. Yeah, okay. And the means corrected matrix, which we really denote as XC1 and XC2 for computed like this. Very simple. All we need to do is for X1, just do 4, what are the value 4 in this case, minus the overall mean, which is 5.7. We'll use this individual means later, not now. So for now, it is the data point value minus the corresponding mean. So for X1, it's 4 minus 5.7, that is negative 1.7. And for X2, it is 1 minus its mean, which was 5.6. So 1 minus 5.6 will be negative 4.6. Similarly, it is 2 minus 5.7, so that is negative 3.7. And 4 minus 5.6, it is negative 1.6. So what we could do is, we could automate this by just doing something like this. So this is A2. You'll see this will be A2 minus 5.7. This is B2 minus 5.6. And you can copy and paste and do only for those 5 records. That will get you the means corrected matrix for class 1. Similarly, you can get the means corrected matrix for class 2 by using these five records. So that will be, in this case, from A7 to A11 was my class 2. So A7 minus 5.7 will be this one. So that, and this is B7 minus 5.6. And you can copy and paste to the other cells, you get the corresponding difference. So that's the second step, to find the means corrected matrix for each class. And the third step is to determine the product of the means corrected matrix and its transpose. You know what transpose is? So this is our means corrected matrix for class 1, XC1. If you transpose it, the columns become the rows, and vice versa. It means the rows becomes the columns. So you can say this row, negative 1.7, negative 4.6 becomes the column. Or you can say the column becomes the row. So either way you can consider that. So we have here 5 rows and 2 columns in XC1, and the transpose has 2 rows and 5 columns. And then you're doing the matrix multiplication. Now, there is an online calculator for matrix multiplication. Same site that was hosting the Gaussian elimination is having that as hosting a calculator. So let me work out one thing, and you can use this calculator. You don't need to do the matrix multiplication on your own. So you have to specify the dimensions though. So by default, it will load up as a 3 by 3 matrix. So the first, remember, notice here, we're multiplying the transpose with that matrix. So first is the dimensions of the transpose matrix, which is 2 rows, 5 columns. So you have to make it 2 rows, 5 columns. And the other matrix is going to be 5. The other matrix is going to be 5 rows, 2 columns. 5 rows, 2 columns. So this matrix is 5 rows, 2 columns. And now you can enter your values. So for the matrix, the first matrix is negative 1.7, then negative 3.7, then negative 3.7 again, negative 2.7, negative 1.7. Then it is negative 4.6, negative 1.6, negative 2.6, 0.4, negative 1.6. For second matrix, this is this one, the original one. So that's negative 1.7, negative 4.6. Make sure the negative entries are getting entered correctly. Then negative 3.7 and negative 2.6. Negative 2.7, 0.4, negative 1.7, and negative 1.6. So once you enter the values, you can click equal to here. It's going to do the math and give you the result, which is 40.45, 25, 25, and 33.2. That's what I have here. And then what you do is, once you get the actual product, then you divide the entry, each entry in the product matrix by the number of records for this class. So this class 1 has 5 records. So we divide each of these entries in the product matrix by 5. So 40.45 divided by 5 is 8.09. 25 divided by 5 is 5. Again, 25 divided by 5. Then 33.2 divided by 5 is 6.64. So this is what we need to find as a result of this step. Okay, so do the same thing for class 2. So this is a main skirted matrix that we had for class 2. So first get its transpose written correctly, and then multiply with its with that matrix. So this is the actual XC2. So its transpose is going to be, the first column becomes the first row, the second column becomes the second row. And then you enter the data for multiplication. So you go back, and since we have the dimensions already set, it's just that you have to correctly replace those values. Make sure you don't do any mistake in that. So make sure the negative values are highlighted and replaced. So this is 3.3, this is 0.3, 3.3, 2.3, and 4.3. This is 4.4, 2.4, negative 0.6, 1.4, and 2.4. And here this is 3.3, 4.4, 0.3, 2.4, 3.3, negative 0.6, 2.3, 1.4, 4.3, 2.4. That's equal to, okay, get 45.65, 26.8, again 26.8, and 33.2. Again, this class has 5 records in the given data set. So you divide each of these entries by 5. 45.65 divided by 5 is 9.13. 26.8 divided by 5 is 5.36. 33.2 divided by 5 is 6.64. So that's the step 3, to determine the product of the transpose and of the mean scatter matrix with itself. The next step is to determine the covariance matrix and its inverse. So how we determine the covariance matrix is, so this is the result of the previous step after you divide by number of records, the product matrix. So we call that as the kind of covariance matrix of individual classes. And then what we do is we'll determine a weighted average of the entries based on the number of records belonging to each class. So nothing but what we need to do is, so we need to determine, this is the covariance matrix. So how we get these entries is, so here we have 8.09 from class 1, and class 1 has 5 records. So we take the fraction, that's like a weight, 5 of the 10 records are for class 1. So it is 8.09 times 5 over 10. Plus this 9.13 comes from class 2, and it has 5 of the 10 records. So take a weighted average. So this is called the weighted average. So it comes out to be 8.61. So it's kind of in between the two. Okay. Similarly, you have 5 records from class 1. That's that entry, and 5.36 for 5 records from class B. So 5 out of 10, 5 out of 10. So to get weighted average, it's 5.18. And it's also 5 and 5.36, so it's going to be 5.18 here. Then it's going to be again 6.64 and 6.64. So it's going to be the same 6.64. So this is the covariance matrix for the entire data set. Okay. And then we need to take the inverse of that covariance matrix. And this is matrix inverse. So what is the idea behind matrix inverse is, with numbers, say for example, if x equals 3, 1 over x is the inverse of x, which is 1 over 3. So if you multiply x with its inverse, we get 1 with the numbers. Similarly, with matrices, we can have a matrix multiplied with its inverse. We say a to the power of -1 in general for inverse in math, but this is what convention sign I follow here. So we can use the same sign. I think I say the C inverse. C inverse, okay. So if you multiply A with A inverse, so this is a matrix. So again, depends on dimension. Let's say A is a 2 by 2 matrix. 2 rows and 2 columns. So then, if you multiply the matrix with its inverse, you should get what's called an identity matrix, which is going to be 1, 0, and 0, 1. So the leading diagonal will have ones. So if it's a 3 by 3 matrix, if you multiply a matrix with itself, the product will be an identity matrix like this. So this is an identity matrix of 3 rows and 3 columns. Okay. So here we have a 2 by 2 matrix, which is this 8.61, 5.18, 5.18, 6.64. So if you take its inverse or compute its inverse, this is what we get. And there's an online calculator as well. The same site, we can use the same site for everything. There's another site which I used to use before, but we'll use this site that we have been using. So if you go type that URL, they're pretty good, easy to enter and get the result. The other site is little kind of comparatively tedious, but this is more easier. So this is a 2 by 2 matrix. Again, you can find inverse only for square matrices. So that's why they already coded like 2 by 2 or 3 by 3 and so on. So let us enter this matrix, which is 8.61 and 5.18. This is LDA is just math. You have to just follow the steps and the math, and you'll get the result. So the A inverse is this, which is good here. So like the Gauss elimination, they give the result in fractions, but we can get in numbers. So 3320 divided by 15169, you can use a calculator to get the value is 0.219289. Similarly, the other values are going to be negative 370 divided by 2167 is going to be negative 0.1707. It's the same entry here as well. And then 615 divided by 2167 is going to be 0.2838. Okay, so that's the inverse of C. So this is the C, the covariance matrix, and you get it by taking a weighted average of entries in the individual C1, C2, the covariance matrix, and then the C inverse. Okay, so that's step 4. Then step 5 is to determine, so we're almost done. So we need to now determine the coefficients for each class. So you see here, once we get into this, the number of records or the number of features in the data set doesn't really matter. What shows up is a 2 by 2 matrix because, or basically 2 by 1 or 1 by 2 or 2 by 2 because the number of classes is 2. If you're dealing with 3 classes, you'll have like 3 rows or columns like this. So that's kind of like dimensionality reduction that this approach does. Okay. All right, so now we are going to use the mu values from each class. So the mu class 1, so this 3 is the mu of x1 just for class 1, and 3.6 is the mu of x2 just for class 1. So if you go back and check, this is what we have tabulated. The x1 mu for class 1 is 3. That means Just among the class 1 records, the average of the x1 values is 3. And just for the class 1 records, the average of the x2 values is 3.6. And that's kind of, you're going to use as a 1 row, 2 column matrix. Okay. As a vector, basically, it's a 1 row, 2 column matrix. Multiply with the covariance inverse. So here I have C inverse, which is this. So I have denoted both the notations. So that's this inverse of the covariance matrix that we just computed. And we need to do a transpose of this matrix that we just wrote. So 3.6, if we do a transpose, becomes like this. So 1 row, 2 column becomes 2 rows, 1 column. So 3.6. So we need to multiply these 3 matrices and we'll get this number. We'll also need to store the result of the intermediate multiplication. So if you multiply these 2 matrices, which is the mu of class 1 times the C inverse, we'll get this matrix. We need to store that as well. So let's again use that calculator to do this. Show for this as well. So this is the one. We're going to multiply these 2 first. So that's going to be, the A is going to be 1 row, 2 columns with 2 rows, 2 columns. So it automatically shows the matrices. So this is 3.6, and this is going to be 0.2189, negative 0.1707, and this is again negative 107, and this is 0.283. So if you click equal to, it's going to give you the product, which is 0.04218 and 0.5096. You can approximate to 4 decimals if you want. So that's this intermediate product. And we have to multiply now this intermediate product matrix with this 3.6. So this is again a 1 row, 2 column matrix. We don't have to change the dimensions here. But the second matrix we're going to multiply is a 2 row, 1 column matrix. So this is a 2 row, 1 column matrix now. So we will now enter this 0.04218 and 0.5096 for A, and then the 3 and 3.6 that we have here for the B, this other matrix, this 3.6. So the result is going to be a scalar because it's a 1 by 1 matrix. So that's 1.9611. And that's what I have recorded here. Okay, so we just did this for class 1. So we need to determine the same thing for class 2. So the mu class 2 basically is a vector comprising of the x1 mu of x1 just for class 2 records, and the mu of x2 for just the class 2 records. And that's going to be 8.4 and 7.6, if you see that here, for class 2. And then this is the same inverse that we computed here. And then this transpose of 8.4 and 7.6. So if you go through the multiplication, this is what we get. And if you multiply this matrix with this 8.4, 7.6, we get this scalar quantity. So these are the 4 things that we need to store or remember for our predictions. So this value for each class, this entire scalar value, which is for class 2 is 10.0426, and this intermediate product matrix for each class as well. Okay, so let us do a prediction for a data point in the training data set itself, and then we will see for all the other data points as well. So 3.6 is the data point in the training data set, and we need to now do a prediction of class, whether it will belong to class 1 or class 2. So we'll compute what's called an F value, like Wx there or theta x in the previous classifiers. We'll call the F value for a function value for each class for a given test record. In this case, that's 3.6. So the 3.6 is treated again as a matrix. It's a 1 row, 2 column matrix. So we're going to compute things like this. So we're going to take that mu class 1 C inverse that we computed for class 1, multiply this with the transpose of that test record itself. So this is a mu class 1 C inverse that we computed here. Multiply this with the transpose of 3, 6. So 3, 6 is written here as 1 row, 2 columns. So the transpose will be 2 rows, 1 column. And the result is going to be a scalar, this. Do the same thing for mu class 2 C inverse, which we computed here. Multiply the transpose of 3, 6, and that's going to be again a scalar. So once we have these values, we are ready to calculate the F value for each class for this test record. So it's going to be this value that we just computed for each class. So this for class 1, we got this as 3.1841 minus half of this value that we computed for class 1 here. Okay, so basically instead of this 3.6, which is the inverse of, or not inverse, the transpose of this means for x1, x2, we use the data point itself. That's the only difference. So to get the first term, and we got this 3.1841 minus half of this value that we got with the means, which is 1.9611. Okay, plus this is like a tiebreaker thing that we use for in the F formula, the logarithm of the probability for class 1, and this is natural logarithm, so base E. So probability of class 1 is 1 over 2. 5 of the 10 records is class 1, so it's 1 over 2. So how to take the logarithm of 1 over 2? Just type 1 over 2, and the logarithm of this is, and of course you can press enter to get the 0.5, and then just press the ln key, you get the natural log value. So all these numbers now are now used in the calculations. So the 3.1841 that we determined for the test record, 3.1841 minus half of that 1.9611 that you determined here for that and class 1. Plus that log of, can say 1 over, so it's 1 over 2 on this term. Plus 1 over 2. Just click the logarithm of that. It's going to compute that. So it's 1.5104. So this is the F value for class 1 for this given test data point. Similarly, compute the F value for class 2 for the same test data point. So this term that we computed with the test data point is 5.9622 minus half times. Instead of this test data point, we used the means and got this number. So use that number. So minus half of that 10.0426. Similarly, plus log of 5 over 10. So that will give you this. So we got 2 F values, one for each class for the test record data point. So the larger of the F values gives the corresponding class. So 1.5104 is greater than 0.2478. It's very clearly you can differentiate between the 2 F values. So this data point 36, we are predicting it to belong to class 1, and it does belong to class 1 in the test data set. So in the training data set, so 36 will belong to class 1. So like that, you can do the prediction for all the data points in the training data set or for any other data point as well. So let us do for a test case as a practice. Let's say we pick something that's not here. I would pick, say, 5.5, for example. Okay, it's not in the training data set. So 5.5 is my X, for which I want to predict the class. So let us go through these calculations that we did in this slide. So this term, I would say I can do this in a PowerPoint slide more easily. Yeah. Okay, so 5, 5 is my test record. So I multiply that with this mu class 1 C was times the transpose. So this should be 5.5. Okay, the transpose of this 5, 5 is this 5, 5 here. So I'm going to multiply mu class 1 C inverse, which is this matrix here. Yeah, better use that here itself. I didn't add the test case. It's better I do that here so I can include that in the slide. Testing for yep. Which is 5, 5. All right, so yeah, that's the last step. So we can do that here. All right, so this multiplication, let's see what we get. So this is 1 row, 2 column with 2 rows, 1 column. So we have that, and we have the main entries as well. This is 5, 5, 5, 5. So this is coming out to be 2.7589. Similarly, this is the mu class 2 C inverse for the second class 2. And again, the same 5, 5. We have to use that here. So let's go back here and change the entries to 0.54, 0.5414, and 0.723 is equal to, we get 6.322. So for class 1, the function value is now going to be 2.7589 minus half times the same. So these things don't change. This value we determined for the entire class 1 previously here, the 1.9611. So it's just that instead of the 3.6, the means vector, we used the actual data point. So that's the difference. And that's the first term here. We got this as 3.1841 minus half times 1.9611 plus log of 5 over 10. That's also not going to change because the training data set has 5 of the 10 records for class 1. So let us compute this value though. So this is going to be, this is not the slide. Yeah, so 2.7589 minus half times 1.9611 plus log of, plus 5 over 10. Take the natural log of that. So that's going to be 1.0852. Yeah, that memory. Okay. And for the second one, that's going to be the 6.322 minus half of times the value here we got for the entire class 2 plus log of 5 over 10. So everything else remains the same. Minus half times 10.0426 plus 5 over 10 log. So you get 0.6076. So again, the F value for class 1 is larger, so we are predicting that it belongs to class 1. This 5, 5 also belongs to class 1. Its value is 1.0852. You have to change this to 5, 5. 0.6076. So you're doing a prediction that 5 belong to class 1. Like this, you can test for any data point. Okay. So if you plot all the F values, as I showed before, for class 1. So for class 1, we got these F values for class 1, class 2 for each of these data points. And we picked the larger of F values. So for this data point 4.1, we got these as a 2 F values, negative 0.9954 and negative 2.9350. And as I said before, for negative numbers, we pick the actual smaller value with the negative sign as the largest. So this is the larger, and this corresponds to class 1. So the predicted class is also class 1. Between these two numbers, this is largest. So again, this will correspond to class 1. Again, between these two numbers, both are negative. This is the larger value. So that's class 1. This is class 1 clearly, and this is again class 1. As now for these next 5 records, we're going to have this number to be larger than this. So that's class 2 predicted, again class 2, class 2, class 2, class 2. So if you just plot the largest value that we pick, between the two classes, that's the value that we're using which we decide the class, and just plot those F values. So for, say, for example, the negative 0.9954 is basically this data point here. And then this data point will be something between 0 and negative 1. So let us see what it is, 0 and negative 1. So probably it's going to be this one. Okay, so that's this one, and so on. Yeah, yes. So if you plot all the largest F values between the two classes for each data point that was used to decide the class, then you can see that all the blue ones are kind of clustered together and all the red ones are clustered together. So the F values for the data points that are predicted to belong in class 1 are kind of exhibiting closeness, that means less variance. And the F values belonging to class 2, they're not much close, but reasonably close, so less variance. And they are clearly different from across the two classes. So that's the kind of power of this LDA method. F values are just plotted in one dimension, even though you had two features. It's just the number of classes that is at the complexity, and still the F values are just one numbers for each class for each data point. And you just use the largest of the two F values and plot the largest of the two F values. You get a clear differentiation between the data points, the two classes. And that's also because the training data set that you are given with has a clear decision boundary that separates the two classes. Okay, and reasonably separate a reasonable distance between the two classes, the data points. Now we can try this for CRP temperature data set. And one thing the CRP temperature data set is the standard deviation of the two features, as we remember saw the previous module, is different. So the CRP values, which is X1, the standard deviation is 17.80595, which is one of these values, and the temperature values, which is X2, is this. So yeah, reasonably different. So as I said earlier, LDA assumes that the features have same variance, but if they have different variants like this, you can still use LDA. So it's not that LDA cannot be used. It can be still used. The only thing is they may not be able to see a clear separation of the F values of the two classes. They're going to be more cluttered, close enough to each other. And when we see their values later in this example, you'll realize that. So the steps, again, the same steps. The first step is to find the overall mean for all the classes put together. So this for X1 and X2. So this 13.25833 is the mean for all these the 12 records here, 6 for class 1 and 6 for class 2. Again, we don't need to follow any convention. We can get these class numbers, as you can see by now, is just for our reference. So you can even say class virus, class bacteria, and just go through the math. Okay, so the mean of all these 12 records of X1 or CRP value is 30.25833, and the mean of all the 12 records for X2 is 39.033. Then you take the class-wise mean. So for class 1 records, just the first 6 records, the mean of the X1 values comes out to be 19.433. And the mean of the X2 values just for class 1, 6th records is 38.2333. Similarly, for class 2, the last 6 records, the mean of the X1 values is 41.0833. And the mean of all the 6 records for class 2 for X2 values is 39.833. So you need to really determine these values correctly, because as you can see, the rest of the calculations really depends on the means that you find. So make sure you do determine the means correctly for individual classes and across all the classes. So now you determine the first step is the means corrected matrix, which is XC1 and XC2. So basically what you need to do is use this the overall mean. So for XC1, which is basically the 6 records belonging to class 1, so these 6, the first 6 records, 40 minus the mean of X1, which is like 30.2533. And so 40 minus 30.2583 is 9 point something. And 36 minus the mean of X2 was 39.033. That's going to be negative 3.0. So do that for all the records for class 1. Similarly, for all the records for class 2. So again, the same mean, 42 minus the 30.25 is the overall mean for across all classes. And then 39.0333. Okay. So don't make the mistake of using the mean for class 1, X1, and mean for class 2, X2 here. Not in this step. Only in the final step, you use the individual means for each classes. The first step, you make sure you use the overall mean across all the classes to find the means corrected matrix. Okay, so don't do that mistake again. So that's how we find the means corrected matrix using the overall means. Then the second step is to find that XC1 transpose times XC1. So here, the XC1 has 6 rows and 2 columns. So that's the 6 rows, 2 columns, XC1. And before that, you write its transpose, because it's transpose times XC1. So this is the transpose of XC1. So you can use that matrix online matrix calculator to find the product of this XC1 transpose and XC1. So it's 2 rows, 6 column with the 6 rows, 2 columns. You're going to get a 2 by 2 matrix. So here itself is like a dimension reduction. From here, you're not going to look at the individual records. Okay, so this is the product, just the raw product of these 2 matrices. So now you are divided by the number of records for this class 1 that you're doing here. XC1 will correspond to class 1. So there are 6 records for class 1. So divide each entry by 6. So 1644.377 divided by 6 is this, negative 52.869 is this, and so on. Similarly, do for class 2. So this is the XC2 matrix that we got for class 2, and this is its transpose. To the multiplication, this is the product. And again, we had 6 records for class 2. So divide each entry by 6, and that's what you get. So that's the C1, C2, the individual covariance matrices. And now we have to get the overall covariance matrix as a weighted average of the entries. So what you do is multiply each entry by the corresponding fraction. So 274.0628 times 6412, the 6 of the 12 records are for class 1, plus this 307.1988 times 6412. So taking the weighted average of these two, that will come out to be 290.6308. Similarly, negative 8.8115 times 6412 plus this negative 11.3077 times 6412. The weighted average comes out to be this, and this is the same entry here as well. And then there's 4.356 here for class 2, 6412, and then 3.70 to 6412. So that's going to be 4.02889. So that's your C matrix, and then you do its C inverse using the inverse calculator online, and you get the C inverse. And then the last step is to find this product of these three, the mu class in one. So here's where you use the x1, x2 means for the individual class. So we have computed that as 19.433 for x1 and 38.233 for x2. So use that as a row vector. That's the matrix times the inverse overall covariance matrix inverse times the transpose of the same thing over here. So the intermediate product, we're going to record that here, which is this. And this matrix, product matrix times is this transpose of this means is this. So it's going to be a scalar number. Then similarly for class 2, the mean of x1, x2 is this. That multiplied by the C inverse, the same matrix that we use here for C inverse. And that's this intermediate product matrix for class 2. And that matrix multiplied by the transpose of this means is going to be the scalar value. So we need these two, the intermediate product matrix for the two classes and the scalar values for the two classes to do our prediction. So let's do that for a training data set that we have, say, 4036. So we want to do a prediction of its class. So the mu class times 1, so we'll do the we need to do for each class. So for class 1, the mu class 1 times C inverse that we found here is this matrix times its transpose, X transpose, so 4036. So that gives you this value. Similarly, the mu class 2 times C inverse is this that we just found here for class 2 times its transpose, the same 4036 transpose is this number. So now we can ready to compute the F value for each class. For class 1, for this test data point is going to be this 397.8383. That's this first term in this formula. If you notice here, that's this first term. So that's here. Minus half times the mu class 1 C inverse times mu class 1 transpose, which we computed here for class 1 as 412.5453. So that's what we have here, means half of that 412.5 plus here 6 of the 12 to be class 1. So log of 6 over 12. And if you do the math, you get 190 point something. And for F, for class 2, for 4036, you get 424 here, 0.68, minus half of this 468 that we computed here for the entire class 2, plus log of 6 over 12. So this is the number we get. So you see the difference is kind of close, considering the numbers are big. The F values for the two classes are reasonably close. But still, we have to go by the magnitude. So 190.8725 is greater than 189.8772. So we say that data point 4036 will belong to class 1. So I can do a similar prediction for all the data points, and we'll observe that the predicted class is the same as actual class in the data set. So there's no discrepancy. And if you notice F values, so this is the one that we just did. This is larger, so class 1, again 191, 188, class 1, say here is 218.76 and 218.14. So here is where you have to be very careful with the calculations. A small difference could make a wrong prediction. So we'll still go with the math. So this is the largest value, and that's class 1. And then for class 2, you see this 208, 254.66. Again, the numbers are reasonably close. Okay. So this is also where I said, because the variance among the features is reasonably different, that's why you're not able to clearly differentiate between the two F values for the classes. So you get them to be reasonably close like this, but still it's doing a right prediction, correct prediction, because it picks the largest of the two F values, and you get the correct prediction. And also, if you plot the F values, the largest of the F values for the two classes for each data point, I think there will be some overlap, because you see here you got a 218 and 214 and 223 or 224 as well. So these three numbers are larger for class 1 for these three data points. And you will see some 208 here and 223 here for 222 here as well for class 2. So there's overlap in the F values that you come up with for the predicted class. You didn't see that in the first example though. That's because the variance is comparable and you had a clear separation boundary. As if you remember the separation boundary for or decision boundary for the CRP temperature data set, it is a clear decision bound, separate decision boundary, or but you see this is what it is. The data points are kind of close enough to each other if you plot them. It's not a clearly visible, even though there's no outlier. The two classes, the decision boundary is kind of narrow. So you can say it's a narrow margin, a decision boundary. So that's also a reason why there's overlap on the F with the F values. But still, you're able to do a correct prediction because you're still going with the larger F value that you are computing for among the classes and deciding based on that. We'll see one last slide or example. This is for multi-class classification with LDA. As I said, we don't have to do any tweaking. LDA by itself is designed for multi-class classification. So this is that last example that we saw for support vector machines, a module as well, where you had class A, B, C, and you had, so I have visualization there. 4 data points for class A and 3 for class B and 4 for class C. And here I have visualization only for the normalized version, but it's almost the same for the raw data as well. So let us see what LDA does with this data set. And again, remember with LDA, you don't have to do any normalization, just go with the raw data. So if you find the standard deviation of X1 across all the classes, and for X2 across all the classes, you get 1.19 and 0.84. So the standard deviation or the variance is kind of comparable. So this is a better data set compared to the CRP temperature data set. So now we need to determine the mu across all the classes for X1 and for X2. So that means across, so here we have 11 records, 4, 3, and 4. So 4 plus 3 plus 4, 11 records. So of the 11 records, all the add the X1 values and divide by 11, that's the mean average of all the 11 records. Similarly, average of X2 among all the 11 records is going to be 1.9909. And then find the individual means for each class. So the mean of the 4 class 1 records for X1 and the mean of the 4 class 1 records for X2 are going to be 1.3 and 1.05. Similarly, just for these 3 class 2 records, you find the mean for X1 and the mean for X2. Similarly, for these 4 class 3 records, find the mean for X1 and the mean for X2. So once you find the means for each class and the overall means for all the 2 features, we are ready to find the means corrected matrix. So here we're going to have 3 means corrected matrix, one for each class. So XC1 is going to be like just for these 4 records. So it's going to be again the overall mean. So 0.5 minus the overall mean is what's that? 2.327. So 0.5 minus 2.327 is negative 1.827. Then this 0.5 for X2 minus this 1.99 is negative 1.49. Similarly, this 1.5 minus 2.327 is negative 0.827. The 1 minus 1.99 is negative 0.99. And this 2.5 minus again the 2, again, make sure you use the same overall mean for X1, X2, get these XC1 matrix. Now for XC2, just these 3 records. So this 1.7 minus 2.327 is negative 0.627. This 2.1 minus this 1.99 is 0.109. Then this 2.3 minus 2.327 is negative 0.027 and so on. And this 2.5 minus 1.9 is 0.509. So that's for XC2. XC3, the last 4 records. So 3.1 minus 2.327 is 0.7727. Then 2.1 minus 1.99 is this 0.19. Then 3.5 minus 2.327 is 1.1727. Then 2.3 minus 1.99 is 0.309 and so on. So do that for those 4 records, you get XC3. So the second step or third step, so I count finding the means as the first step. So after you find the means, you find the means corrected matrix. So find the means corrected matrix is the second step. Now step 3 is to find this product, the XC1 transpose times XC1 for each class. So these are the 4 records for XC1, the means corrected matrix, and take the transpose first. Again, remember that you have to first take the transpose and then multiply by that actual matrix XC1. So do the multiplication, you get a 2 by 2 matrix here. So, and you divide these entries by the number of records for class 1. You have 4 records for class 1. So divide the 6.701 by 4, you get 1.675, then 4.206 by 4 is this, and so on. Do the same thing for the other 2 classes. So this is the means corrected matrix for XC2, and this is its transpose. So multiply by the transpose by the matrix itself, you get this 2 by 2 matrix. Divide by, again, there are 3 records in class 2. So you divide these numbers by 3, you get this matrix. Do the same thing for class 3. You have 4 records there. So divide each entry by 4, you get this. And then you have to do a weighted average. So here's where to be careful because you don't have an equal number across the classes. So these are the 3 matrices for each class. So the weighted average is going to be like this: 1.67529 times 4 out of the 11 or for class 1. Then plus this 0.16108 times 3 of the 11 or for class 2. Plus this 1.734834 times 4 of the 11 is for class 3. So if you do the math for this, you get an average involving weighted average of these 3 numbers, which is 1.2856. And that's what you're going to record here as the covariance matrix, overall covariance matrix. You do that for each entry. So this 1.051571 times the 4 over 11 for class 1 times negative 0.13752 times 3 over 11 plus the 0.799752 times 4 over 11, you get 0.6357. Again, the same entries here in this cell as well, so you get the same 0.6357. This cell 1.01781 times 4 over 11, and then 0.42978 times 3 over 11 plus 0.42712 times 4 over 11, you get 0.6426. So record those entries, that's the overall covariance matrix, and then use the inverse calculator to find the inverse of that, C inverse. So once you get the C inverse, you're ready to compute this quantity, and you also need to compute the intermediate product matrix. So mu class 1, so now we pick up the means that you computed for x1, x2 for the individual classes. So 1.3, 1.05 are the means of x1, x2 for class 1. You pick up that. That's this row vector times the C inverse, which we just computed here. And do that multiplication, that's this intermediate product matrix. And multiply this product matrix with the transpose of this 1.3105, you get the scalar quantity. Do the same thing for the other 2 classes. So this is the mean of x1, x2 for just class 2. And multiply by C inverse, you get this product matrix. Multiply that by the transpose, you get this number. Then do the same thing for class 3, the means for x1, x2, and multiply that means vector with the C inverse, you get this product matrix, multiply this by the transpose of the mean values, and you get this 11.712. So once you have all these numbers, you're ready to do the prediction. So you just need the overall scalar quantity and this intermediate product matrix for each class. Okay. So let's pick up a test data point from the training data set. So 0.5, 0.5. So you're going to get the product matrix for each class and multiply with the transpose of 0.5, 0.5. You get the scalar quantities. And now use those scalar quantities as a first term of this formula equation here. minus half times this numbers come from the other scalar quantities that you find here using the mean values of x1, x2 for each class. So 1.8196 for class 1 plus log of 4 over 11 because you had 4 of the 11 records for class 1. Similarly, for class 2, the same test data point, you got 1.96702 minus half of this 10.3773 comes from this thing here that we found for class 2 plus a log of 3 over 11 because there are only 3 of the 11 records for class 2. Then for class 3, we found 1.9736 here. So that's the number we use. Minus half of 11.7712. That's the number we got from the mean values. Plus log of 4 over 11 for class 3. You get this number. You see the F values. So among the F values, we pick the largest. And this all the 3 F values are negative in this case. And we pick the largest of the negative values, which is negative 1.1023. And that corresponds to class 1. So we say this data point will belong to class 1. You can do the same thing for all the data points in the training data set. And so you get the F values for each class 1, class 2, class 3. So among the 3 F values, you have to pick the largest, which is this one for the first data point. And again, these are negative. So you pick the largest, which is this. And the largest is going to be this again for class 1. This is the largest again. This is the largest here. So that's class 2. And you see the actual class is also class 2. So there's no contradiction here, especially this data point in the support vector machines topic, 0.71.5. When you look at the normalized version, the visualization, this one, 0.71.5. I think that's what it is. Yes. No. This one. This one is this last of the class A record. So negative 1.368 and negative 0.588. That's one. So this one, when we did the support vector machine, if you remember, for this data point here, the fourth data point in class A, the W times X value, it came out to be 1 for class A versus rest. But for class B versus rest, it came out to be 1.165, a little larger than the W times X value for class A. So going with that convention, we pick that class for which the W times X value is the largest. We kind of said this data point is predicted to be in class B, but it's actually in class A. So that's the discrepancy that we noticed in support machine. But LDA does not have the discrepancy. It is the predicted class for this data point is class 1 itself, which is class A. Okay. So for all the data points, the predicted class is same as actual class. That's good because this is the training data set and we used all the training data points for building the model. And it is predicted, the predicted class is as expected for the actual class. And also, if you notice the F values here for class 1, the F values, the largest of the F values are still smaller numbers like this, 0 point something, 0 point something negative. And for class 2, the largest of their values is like 2 point something, 3 point something, and 6 point something. And for class 3, it is 3 point something, 4.5 point something, 6 point something. So even though there's some overlap between class 2 and class 3, there's clearly this differentiation between class 1 F values and the class 3 and class 2 F values that you notice. Okay. And even for class 3, the F values are yeah, it's not 2, it's 3 and above. So, but still, I would say it's an overlap. But it's better than CRP temperature data set though. So we can use the same approach and do a prediction for any test data point if you want. Let us just pick up for curiosity one data point that we observed here. Let us say 2.62 and 2.2. Let us do that, 2.62 and 2.2. So testing with arbitrary data. 2.62 and 2.2. So this is 2.62 and 2.2. So of course we need to find the result this thing. Okay. It's 2.62 and 2.2. Okay, so you need to multiply with that transpose of 2.62 and 2.2 here. Let's use this guy. So this is 1 by 2, so we have it set up already. So 0.397844, and this is 1.240414. This is 2.62 and 2.2. And comes out to be 3.77126. And then this one again is 2.62 and 2.2. Oops. Let's change that row into negative 0.70689. Okay, 4.70473. We're at 8.3122. And then this one we can approximate to 4 decimals. This one we have to multiply with 2.622. So that's going to be 1.678192. This is 2.269176. And this is 9.3890. Okay, so 9.389. Okay, so now we have to use these values. So we got 3.7713 here. And then with half of what we got here is 1.8196. So those things don't change. And so the answer is going to be 3.7713 minus half times 1.8196 plus logarithm of 4 over 11. So that's going to be 1.8499. 1.8499. This 2.62 and this 2.2. We got 8.3122 for class 2. And the rest numbers will not change. So 8.3122 minus half of 10.3773 plus 4 over 11 logarithm is 2.119. 2.1119. So 2.1119. Okay. And there's 9.389 here. So that is 2.62 and 2.2. 9.389. Minus half of this. Yeah, that doesn't change. So 9.389 minus half times 11.7712 plus this 4 over 11 logarithm is 2.4918. 2.4918. So the largest of the three F values is 2.4918. So we can say it will belong to class C actually, or class 3. This is for class 3. So 2.4918. So 2.62, 2.2 is predicted to be in class 3. Whereas in support vector machines, it was predicted to be in class 2, I guess. Predicted to be in class 6, class C, that's good. The support vector machine also is predicting to be in class C. So, and LDA is also predicting to be in class C, which is class 3 here in LDA. So it's good that so you can compare. So it's good to see that this data point is predicted to be in class 3 and it is predicted to be in class C, both classifiers. Okay, so that's kind of the consistency you would like to have across the classifiers. So it doesn't matter which classifier you use, you would like the prediction to be the same for which class the data point belongs to. Okay. All right, so with this, we stop this video and we finish the LDA module.